first of all, maybe I should point to Joshua Pierce here. I have him on another tab. Joshua Pierce, he's the one that instigated the project. We've worked in the past with Joshua on a scientific instrument for photovoltaic cells. He came to us because he wanted to develop it in a sort of an open source mode. He needed a community around the project. That was in 2017. And I know Joshua because we're part of some networks, some communities. And he's a champion of open source software, open source hardware development. That's what his lab and his students do. They identify high impact hardware projects, be it scientific instruments or some others. And they develop the first prototypes and they try to form communities around. So he's the one that instigated the project in Sensorica. I should say that from the start. And it's a quite ambitious project. I mean, we didn't expect to be where we are today, and that's the magic of open networks. You know, you throw something in, and who knows what's going to come out of it. And there are different reasons why we arrived at this particular design and extruder. Okay, in the beginning we thought we're going to have a blender, throw some leaves inside, shred them into small pieces, and then a batch process, you know, squeeze the juice and boil them and extract this curd, these leaves extract. But a few weeks into the process, we thought that this would be the better way to go, would have greater chances to succeed. But the technical complexity it's a little higher. So, you know, I think this is a nice forum to discuss about these technical challenges, right? Feel free to share this presentation and use it however you like. It has a Creative Commons license. In case somebody wants to dig deeper into the project, which I think would be wonderful, you can click on these Google Drive documents on the NRP processes. So there's a bunch of links on this site here, on this page here. So if this is clickable, if I click on that, it'll open the associated document with that particular process, right? So feel free to explore. Good. So going a little down. So the deliverable of this project, and it's not just a project, it's more a venture than a project. It's not just a hardware project. We are focusing on building this particular deliverable, a machine, an extruder, but at the same time, we're putting in place the processes necessary to sustain not just the development, but also the deployment in the field of this kind of machine. So it's more a venture than a hardware project, okay? But just if you focus on what we want to build this particular deliverable, when we started to look into these things, we realized that, you know, you have to look at the whole chain. What is this thing going to produce? And based on what you want to obtain at the end, the sort of final products, how is this curd being going to be used? That will influence the machine, the architecture of the machine, okay? Because the end way of delivering as a finished product, how is this thing going to be consumed, is related to the properties of the main ingredient, the initial ingredient, which is the powder or the curd, its stability, solubility, you know, all these properties, particle size, viscosity, and that drives how the instrument will be created. And also it depends on what you put inside, what kind of leaves are you using, and you know, there are other characteristics of these sources that might impact the architecture of the machine. For example, the source, the availability of these fresh leaves. If you're working in a place where you only have access to leaves 2 months per year. You have a machine on your hand that you might want it to do something else. So you see how these things can impact the architecture of the device. So you have these axes that generate some requirements for developing this device. And I put them here into a more explicit form, taking into consideration what David shared with us in the email. So I sprinkled his points all over this slide here. These are considerations that you need to take into account when you think about this kind of design. And then there is another dimension of consideration that come from, for example, the environment in which this kind of machine will be used, the ecosystem, other things that are in the environment that this machine will interact with, for example, the power grid, if it's something electrical, maybe other type of devices or facilities in which the machine would be used. The economic model, we can think of the economic model that will sustain the production, maintenance, and distribution of this kind of machine, its life cycle. You have a table here about all these, what we call design considerations that we need to think about when designing this kind of food processing device. I'll not go into much detail into that unless you have questions, but we're going to come back to some of these dimensions when we discuss the economic model that we're putting in place, because this is something new, quite new with Sensorica. It's the innovation model in the economic model. So very rapidly, we stumbled on David's work with Live for Life. We were initially inspired by this batch process that they were using. And this became the base on which we could start thinking forward about extraction of leaf protein. And so the way forward, we thought, is by having the process be done with an extruder. And that was an interesting discovery, looking at the versatility of this tool. You could already use it as a conveyor, a mixer for grinding stuff, texturing, heating. You can have some heating and cooling processes inside, pH change. You can use it for patterning. So you have a few examples here of how this kind of machine could be used. So, right away we thought this is the tractor of food production. This is something that is versatile, and it's probably worth spending a bit of time and understanding its potential in the extraction of protein from green leaves. We like the fact that this device is versatile because of the economic constraints. When we spoke to David, we had access to their project and to the problems that they faced beyond the technical. Okay, how do you get these devices in the hands of people to be successful? Is there an economic model that can sustain its use? And so we understood that if we only focus on one function, which was extraction of leaf protein, then the device could be successfully adopted and used in very specific circumstances. Okay, so in order to have something that could be adopted on a massive scale, we thought that the best thing is to have the function of leaf protein extraction put together with some other possible functions of the device. So the device could be used, for example, the whole year, and there can be greater economic motivations to build it, purchase it, maintain it throughout the year. when this project was presented to us, was essentially presented on this humanitarian angle. Let's bring it to places that where there is problems with nutrition, and allow these local people to extract proteins from the local sources that they find. They might be cut off from global supply chains. Give them the technical ability to tap into this latent capacity of protein. Might be just plants that just grow wild around these areas. So the idea of providing this technical capability, it's linked to some economic considerations, right? So how do you get these devices, these processes in the hands of these people? Well, if there are more incentives, if people can use these devices for something else, we can use that as a vector to get this capability in the hands of people. Okay, so maybe some, I don't know, some villages in Africa, they need a grinder, an oil extractor, or something else, or a juice extractor, to be used 99% of the time. And in case of disaster or any type of problem that generates food crises, the device can be easily retrofitted into a leaf protein extractor. Okay, so that is the main concept here. That's why we chose to go with this kind of architecture. So here's an example of a small scale juice extractor that is built on a extruder architecture, and that is commercially available, and it does a great job for grass, for example. Okay, so there's a lot of juicers with, using centrifuge or squeezing. This one is designed precisely for grass and leaves. And you could see from the design, people with technical minds, the design of the auger here, you can see functions of transport, compact, grinding, and pressing. So it has a great ability of getting this juice out of leafy biomass. So that becomes a model that is interesting. And the whole idea now is, can we scale it up, and not just scale it up, but can we make it at the same time modular, so that it can do some other functions. Okay, so that is the technical challenge that we have, that we can discuss here. And this is a table here, going back to it, that helped us essentially compare what we call the classic process, batch process, to the extruder process, and choose the extruder as the way to go. Okay, so you can go through this table, or if you're interested, we can discuss it later. Like, why did you choose to go with the extruder and not with the batch process? Okay, so we can go through this table and see.
What's the meaning of the numbers on the two left columns?
It's a sort of a score that we gave. So in terms of versatility, we thought that the extruder would score 5, and the batch process would score 2.
So 1 is low versatility, and 5 is high versatility. That's it?
Yes, okay. Yeah, that's as simple as that, yes. Yeah. So this is the sort of a general conceptual architecture of this of an extruder pattern design, let's say, and this is what we're focused on for building. So we take away some components. We don't care about the motor and the transmission at this time. We think making something that has a sort of a flywheel and the potential to connect to an existing motor via a belt or a chain would be more appropriate, because we don't know where these things can land. somewhere in the developing world. So we're not focusing on that part, on the power part. We're focusing on how do we get the stuff inside the device and the process itself. What happens inside the barrels, architecture of screws. We're thinking about transport, grinding, and compression to extract the juice, and then heating and compression again to extract the curd. So with some possibilities for injection of hot steam, injection of water, and yeah, separation between liquids and solids.
Just another question, Tiberius. What are you talking about? A single screw or a twin screw extruder?
That is an open question, but we greatly favor single screw device because of its simplicity. And since this is designed as an open source device that could be easily produced locally, we think simplicity of design leads to greater local manufacturing possibilities. Yeah, so I think aiming for a single screw is a good target.
Yeah, because my question was about the capacity of the extruder to
yes.
to pump liquids with a single screw. You know, with single screw, what we know is that we are limited by the maximum water content, which is it's possible to pump into with the extruder. Usually, you cannot extrude materials with water content with higher water content with water content more than 30%. So I wonder, how do you think that you may pump liquids with the single screw in the second part of the extruder?
Yeah, that's very interesting. And we're at the design phase now, doing the starting to do the 3D modeling. We have some ideas, but it's again an open question. So the idea here is that if we go back to this example, it does a very good job extracting the juice out of leafy biomass or grass, and the juice is ejected outwards, right? It falls into a container. We have to, in this particular case,
or to revert the process.
Yes, yeah. So this would be the part of the juicer, and then the juice escapes inward through a hollow portion of the screw and gets transported to the second one. Now, in this second part, we only have liquid, right? that's the thing. We only have liquid. So the liquid has to be transported across and heated, most probably with some hot steam. And the screw here has to essentially transport that fluid, right? Knowing that there is some pressure on the other side, the liquid should not escape back and into, the pressure should not transfer back into the first barrel. So that is a technical problem. I think we have a note here talking about that. Need pressure control, adjustable expulsive die. So in order to control the pressure, you need some adjustable outlets here. And we believe we can do some simulations before we can go to the prototyping and do some actual tests. And I'm not the let's say I'm not the lead mechanical engineer. I cannot exactly talk about this solution, but that's why this collaboration is interesting, right? To answer these questions. So let's say the first part, we have a source of inspiration that we need to scale based on available, off-the-shelf juicers. But the second part is our own challenge, right? To find out what to do.
And I'll just mention if the findings indicate that design other approaches are required, then we change approach, right?
Yes.
Yeah. Can I make a comment, Tiberius? Is this a time to?
Yeah, go ahead.
Okay. Yeah. Just thinking out aloud, I think your proposal for the first stage is fine because it is really the same principle as the continuous juicer you referred to. But the second stage, I think it's good to think a bit differently rather than Dominic is absolutely right. Because you really have a liquid phase going in. But if you think about the process of what we are trying to do, it is really a heat exchange operation, as opposed to what we conventionally call extrusion, cooking or expelling something from a solid. Now, in the food industry, you use a lot of different types of heat exchangers to convey liquids and semi-solids, pastes, using, for example, what's called a scraped surface heat exchanger. And rather than injecting steam, you can have a jacket where the steam is, and heat is transferred from the wall into the liquid. So in terms of conveying, you might even think about decoupling the extruder, this process. The first one is a conventional expeller, if you like, but it is conveying the material. And the second stage, you can have a pump between the two because you are really having a liquid. What you can do is you pump the liquid into the second stage, which is really a heat exchanger. But although you start with a liquid, as the coagulation takes place, you end up with a liquid and the whey. Now you convey the liquid and the whey before the two are separated. So I think extrusion may be the wrong terminology here. You can think more about conveying and heat exchange from a process engineering perspective. So you have two units that are coupled together with a pump.
Yes, I think that the concern that we have here is to have a continuous process, and that comes from the requirement of food safety or contamination, and have everything done in a closed environment, let's say.
It could still be done. It could still. I'm still thinking about a closed continuous system, but you decouple the two units.
Exactly.
And you link the two together, and in between you have a pump. But it is a fully enclosed system. But by controlling the flow rates and the back pressure, now it becomes a control problem, because as the product goes through, your viscosity will change. And the other thing to take into account is the functionality of the curd, which is what we want to do, because we are completely changing the conventional process, because this is something I have been discussing with Dominic earlier. You are introducing shear, because as the material goes through the conveying system, whether you use steam injection or some type of scraping action, you're also introducing shear, and that may or may not affect the functionality of the curd that's coming out. So this is really where you had to do a lot of experimental work at a low scale, maybe in the lab and the pilot plant, before you scale it up. But the concept of a closed continuous system is still valid.
Yes.
But the second stage, we have to do probably something a bit different to a conventional conveying extruder.
Normally, when at the end of the batch process, they apply quite a lot of pressure to separate the curd from the the water. So there's a lot of water content there's a lot of water that is trapped into the coagulate, right? And that's why we kept the notion of extrusion here. How would you how do you think applying that pressure to separate the water from the coagulate at the end of the...
So it needs some thinking. I mean, you may have to have some type of a sieve to separate the two, so the solids are conveyed and the liquid comes down. So you just have to re-engineer it in a different way and think about
Yes.
what are you trying to do. You're pumping, you're heat exchanging, you are separating. My colleagues who are more of experts than I am, Pablo and Dan Yang, might like to comment about this. So what you really need is a bit of brainstorming, and you can do some simulation on paper or on the computer. But I think eventually you may have to make a little prototype or different types of prototypes in the lab, and then the pilot plant, and then full scale, about how these different unit operations are done in a continuous way.
Yes.
And balance all the flow rates and the heat transfer together as the phase changes from liquid into semi-liquid into separation.
Yeah, so essentially the project is in this zone here, right?
Exactly. The first part is straightforward.
Yeah.
It is exactly your example of a continuous screw from commercially available. You are just scaling it up. The challenge, I think, is the novelty, the innovation. I think is the second part. But again, the different unit operations are not new. It is combining the two together. And the third challenge is coupling the two to make it a continuous process as the rheology changes and as the back pressures change, because, so that they are not two distinct processes, but they are coupled into a continuous process. And ensuring the product quality and the functionality is not adversely affected, because the process we are talking about now will be very different to the batch process in terms of shear effects. Pablo and Dan Yang, do you have any comments? I mean, I'm talking from
I
the
think
top
that
of my head.
in that second, sorry, can you hear me?
Yeah.
Yeah. I think that the concept is make reasonable, and the only thing we need to do is that the second stage is happening is heat coagulation, and also dewatering should happen in the second section. So basically the juice is coming back to that screw inside and is being heated, and then the protein is coagulated and the water is removed, and then the curd form and the curd is concentrated all happen in that section. So the design of that section need a lot of the thinking and the triggering. It is not say impossible, it is possible, but how to design that section, it's need a lot of the engineering, and also maybe different leaf protein, and then we'll need to have a different configurations, depends on the protein, the temperature of the required for coagulation, and the timing as well, how fast they will be coagulate.
Yes, yes.
So there should be a lot of process control and instrumentation in real time. So as well as the mechanical engineering, I think there's some control engineering there too. And indeed, this is a classical food engineering problem, because as I indicated earlier, all these processes will affect the product quality and the functionality. So, and as Dan Yang said, that may also depend, it may vary from raw material to raw material and may not be a generic solution. So the design has to be flexible.
That's right. It will be a combined effort. It will be combined effort of a protein chemistry and mechanical engineering and maybe some sensor.
Yeah. Dominic, what are your thoughts?
Yeah,
Well,
I agree with you, but my main concern is about the second part of the equipment. I agree for the first one, which is a traditional juicer screw profile. But then in the second part, I think in my view, it's not possible to do it with a single screw, because with a single screw, the channel is open. So if you have a high pressure at the end, at the die, just to help expelling the water from the cake, I think the flow will go back, and because the single screw doesn't have this drag capacity that a twin screw extruder has. So I don't, in my view, it's not feasible. Maybe the only solution would be to insert in between the two sections a pump, like a gear pump or something like this,
I think it's
just to develop pressure and to pump the product. But then I think I don't see the advantage to have a screw in this second part, because with you won't have you won't have the capacity to develop shear, because the viscosity should be very low, and the screw profile is not effective to pump the product through the die. So I think what would be better would be maybe to insert a pump, sort of gear pump, just to propel the liquid into the heat exchanger, and at the end to have a sort of filter, just to squeeze the cake and the curd and the liquid. But I don't see the advantage or the rationale to have a screw profile in the second part. If we have if we keep the single screw choice, which is the most the less expensive and the less difficult to design. You know, for even with twin screw, when you handle very low viscosity product or higher viscosity product, but at very high pressure, such as when you want to texturize plant proteins in very long dies, very often you need to insert a pump in between the extruder and the die, because the extruder itself doesn't have the capacity to develop enough pressure to pump the product through the die, even for twin screw. So I don't think it's feasible. I don't think it could be feasible for.
Can we see this as a sort of a reservoir and the screw as shovels? So this part of the screw just shovels whatever coagulate you have formed, shovels it forward, while the fluid can escape back. That's not a problem, because then you can have a sort of a way out for the fluid that accumulates. And then as you shovel this thing towards the right side, you compact it. So let's suppose that the screw gets the distance between the the threads gets smaller, so that you're starting to compact it, and now you're accumulating.
but with a single screw, it's not. This is not possible because the product will flow back because the channel is open. You know, if there is a high pressure which is necessary to squeeze the mix, then due to this high pressure, the liquid will go back.
With
Yes,
the proper
that's fine.
design,
It's fine if the liquid
I
goes
think
back.
it should be okay. That shouldn't go back because that you have a pressure at the back. There is a high pressure during the juice expel. If you can utilize that pressure to push the liquid forward, and that will be generate enough pressure to let the liquid moving forward without extra pump.
I wonder if we can do 3D prints, you know, as a sort of a low-cost proof of concept using a sort of just a plastic miniature extruder.
This is something
I don't
Pablo,
think
you
that's
might like to comment, because there are now CSR has some expertise in computational fluid dynamics or multi-phase modeling, where you can simulate the whole thing on a computer. Pablo, do you want to comment? Is this something that somebody like Kai will be able to have a go at without building equipment to simulate it through modeling?
I think we need to first prototype it and test do a few trials to prove the concept. I think there's the fundamental aspect of, you know, liquid transport and current formation. I think it needs to be sorted first. So I don't know. Is this, and you were discussing about the reservoir. I mean, if you can push the liquid through and at the same time, create the coagulation and squeeze out the liquid, and I guess that's what it is. Is there a peristaltic system or something that will squeeze it and, you know, and remove the liquid, or can we come up with another system that then will feed into something else? But I'm not really sure if CFD modeling will resolve this, Jay. I mean, it will just be it needs to answer a specific question.
Yeah, what I was trying to get at, Pablo, is, I mean, there are two approaches. One is you can physically build prototypes, try it out in the lab, and then you can scale it up. That's one approach. Other one is what's called rapid prototyping, without actually physically doing it. Can you, because this is really a heat, mass, and momentum transfer problem, isn't it? Where whether you can mathematically simulate different simulations, so that you still have to, I fully agree, you still have to do the prototyping, but can you reduce the number of prototyping by doing some initial mathematical simulation, by making various assumptions? I don't know. It's I'm thinking aloud, but maybe it's more practical to build something small scale and try it out. Yeah, with different screws, different sieves, etc. I don't know.
We can, so as I said, we can even try to 3D print a very small scale model of this, where we feed a sludge inside, let's say, and it's all plastic, but just to see the fluid dynamics inside. And if we're able to shovel the more solid part forward, because I have the impression that these coagulate, when it starts to coagulate, we have very clear two distinct phases. Okay, there is no continuous sort of I mean, just from seeing I might be wrong, but just from seeing the process in video, you end up with very distinct phases. So the coagulate could be shoveled forward, let's say, and gradually compacted to the point where the screw, the end part of the screw can actually grab it and push it and press it into the latest part of squeezing, you know. And at that point, the squeezing, you know, the fluid can go backwards, and escape through some filters. It doesn't, but at least that hypothesis, what I'm trying to say here, that hypothesis could be tested out. Maybe with just a small scale, all plastic 3D printed model. And from the feeling that we get from that, we can go to some modeling to feed some parameters into some modeling.
But I think the challenge, Beres, is the rheology, because the rheology of plastics and the two-phase way and curd will be very different, and other challenges. It's time dependent, because to begin with, in the second phase, you have 100% liquid, and as the heat transfer takes place, there's mixing, the coagulation takes place, but the coagulation probably won't be instantaneous. As it goes through, the proportion of solids to liquids will change, and therefore the rheological properties will change as a function of position.
Yes.
So there are many variables, and I think it will be very if you were to simulate this with in practice in a small scale, you may have to use the real thing rather than using a polymer solution or something like that. You know, if you use water and beads of plastic or whatever, that scenario will be very different to whey and the curd. So,
yeah,
but maybe that's a way out. Maybe you had to build some models in a small scale. I don't know. It all comes down to cost. that is a business decision, isn't it? Do it in the small scale and then scale it up. Yeah. So that is part of the development. Yeah.
Tom, you mentioned that instead of using or inserting a pump after the section 1, we can use the pressure that was built up at the end of the screw for the section 1 to push the liquid. Do you have any idea how we could do it? Because in my view, most of the buildup will go to squeeze and remove the solid phase, and I don't see how to use this pressure buildup to push the liquid.
Yeah, the squeezing force can generate a pressure to both sides. One side is a solid phase, the fibrous material that will need to be like expelled out. And if you collect the juice in the closed cavity, and that cavity will generate some pressure.
Yeah.
And use that part of pressure and to push the liquid forward.
Yeah. So it means that you need to develop extra pressure into the section 1 to get some more, which is sufficient to push the liquid into the second part and to the pressure buildup section at the end of section 2. Okay.
The second part at the start is the liquid. To push the liquid forward, you don't need a lot of pressure.
Yeah, but
and when the coagulation happen, and the screw will pick up the viscosity and will pick up pressure and to push the curd out.
Yeah. That's why you need pressure there to squeeze the curd.
That pressure will be generated by the second section of the extruder.
But the problem is then if that pressure at the end of the second stage is greater than the pressure at the beginning of the first stage, or the end of the first stage, as Dominic said, the liquid will go the other ways. It all depends on the pressure drop. The back pressure you generate.
When the pressure, when the pressure generate in the second section,
Yes.
If we lost you, Tom. I think we lost Tom now.
Lost that name. Yeah. He'll come back.
Yeah.
So I think the main take-home message from this discussion is second stage is a challenge. It will need. I think that's where the innovation will be. I think we agree it should be a closed, continuous system, but there are many challenges to be overcome, both on the mechanical engineering aspects and the product quality aspects, and that needs some development work. So I think that's probably the take-home message, isn't it? Whether
Yes.
you do this through prototyping or theoretically or combination of both, I think is a business decision based on funding and resources.
Mhm.
That's right. Yeah, the concept looks like feasible, but a lot development work and testing work.
Mhm. Well, it's good to have.
Can
Yes,
I make
go
a
ahead.
point? I'm wondering if there isn't any value in approximating what kind of a scale you're talking about, because if you don't have some idea how many leaves you're going to process or how many leaves an hour, are you talking about 2 women processing for 4 hours, or how much end product are you going to be able to distribute? It just seems like the idea of a small prototype makes sense, but if you don't have some kind of a target, how many, if you're talking 100 kilograms of leaves, it's a different process washing it than if you're talking a ton.
Yeah.
To just start thinking about what scale is going to really work in places like in Congo, or where there's, because a lot of times they just don't have a forage industry. So you're talking about small farmers with transport problems getting leaves there, and the leaves will quickly start to go bad. If you're not moving the thing through pretty quick. But
Yeah.
Yeah,
I don't know how
maybe
that affects any of the extruder design stuff, but
Mhm.
Christoph, maybe you could make a comment on this. What were your first the first figures that you mentioned about community level processing?
Do you hear me? Because I have a
Yes.
lot of difficulties with it's stopping and
Yeah.
starting again all the time. Anyway, yes, of course, Dave is right. The target is an important thing. Now, another question I'm asking myself is, do we really need to link the two stages, section 1 and section 2 together? Is it absolute necessity? Because it seems to me it's bringing more problems than solutions, and we might have the difficulty of the contradiction between complexity and local and all-in-one systems, because one problem, for instance, would be a contradiction between complexity and cleaning. If you have something which is all in one, it will be difficult to clean, and that's a real concern. Now, we are also avoiding the discussion on alternative concept for the section 2. What is presently working in at
Stuff. I think we lost you.
I can probably fill in here if before he comes back. We thought, David, that the vector of well, the scale is village scale, right? And this was the target set to us by Joshua Pierce, who was at the origin of this project. And we thought that the best vector for dissemination of this kind of device would be the local mills. And we have some partners in Tanzania. This is a real picture on the left here that they sent to us. So I think the processing capacity at that scale, if I understood correctly, is about 2-3 tons per day.
No, that's too high. No, it's much less. I think Christophe will confirm when he is back. It depends how many hours you run the process a day.
Yes.
But
Okay.
yeah.
We see three different scales. The very small scales, Dave will confirm, will be I don't know, maybe 10 kilograms or 20 kilograms of leaves per day. Then another village scale would be more around like from 100 to yeah, anywhere from maybe a maximum would be around 100 kilograms of leaves per day, right?
Well, okay.
And then a semi-industrial scale will be from anywhere around 500 to 1 ton of leaves per day, and that's probably the scale at which the system will be interacting the most efficiently with the environment. And
did you say maximum a ton?
Sorry, say again?
Yeah.
Did you say maximum a ton?
Up to a ton per hour. I'm talking now. It's a lot larger. It's a ton per hour. So if the system is working, say, 8 hours in the day, it will be a lot more. And then beyond that, we are the industrial scale with 50 tons per hour. So are you more interested into the domestic scale, or are you more interested in the village scale or in the semi-industrial scale? For us, the village scale is interesting, but it's difficult to match the funds required.
Yes, we lost him again. I had some numbers here somewhere in the document.
I'll just mention, just in terms of important characteristics of the materials, products, some of the chemistry. I mean, this is area of expertise that isn't central to the folks you're speaking with here today at Sensorica, but I think if there's any way that we can learn canonical information references or some of those key input data that we would need in either modeling or just to also be part of the reality check and the grounding of the design, that would be very helpful to learn about or know where that information can be found. I mean, we learn about the different leaf types, but actual viscosity of curd or actual numbers on that, I don't know, Tiberius, if we've got great data on that.
Yeah, viscosity, not yet, but that's why, we are approaching the food center in Saskatchewan to get some of that kind of information, which we call the fundamental parameters that will feed into the modeling.
I wondered if Jay or Pablo had that information.
On modeling of extruders as not published.
Not the modeling. No, just the like or Dave or anyone. I mean, who's worked with these different devices. Has anyone seen a really good reference of captured data regarding the physical properties of the curd, the physical properties of the liquids, the timing, the heat, all of those things?
There's a lot of information about the the temperature at which the curd forms and the protein levels and stuff. one of the things I think, backing up a bit, is that the curd has a lot of value. It's like a synergistic food. It's much more valuable than just the protein from it. In fact, most places beans are going to be a cheaper source of protein, but it's a it's a fantastic source of iron, because you've taken the fiber out of the leaves, so the bioavailability of the iron and vitamin A is in most places going to be more important than the protein. So I think it's kind of useful to think of it as a as a whole food, or as a synergistic nutrition supplement, rather than the history of it. It got really tied closely to the idea of it's like protein extraction, but it's you're basically removing the water and the fiber from the leaves, and you've got this very nutritionally dense food left. But
Yes.
that's far away from the extruder design.
Yes. Was Dave, when I spoke to you, and we were discussing about the operations in the villages in South America, what was the village scale? I got a number here that I don't remember the provenance, is like 3 tons of leaves processed per day. It's the would be the ballpark of maximum intake of these things, or does it come from you, or?
That would be high for what we did. Was more often around a half a ton a day, or half a ton a day. A day. But we didn't process all day. We typically process half a day.
Okay.
And it was usually women, processing half a day, because if you're grinding leaves for 2 hours, you still have 2 hours of cleanup, and there's a lot of other associated work. If you're running the extruder for 8 hours, you're going to have a lot of work on both ends of washing the leaves and drying the curd, other parts of it. So I would think to be thinking around maybe less than half a ton, maybe up to half a ton for a village scale, partly because it's hard to get more leaves than that and get them through before they start going bad. So there's just a lot of pieces to it that are biological. The other thing is the leaves will vary during the year. During the rainy season, they had a lot higher water content. In the dry season, they had higher fiber content. So the same machine might not necessarily, you might need to adjust it, or you.
Yeah, but talking about these economic requirements that would go into the design, and thinking that the local mills, which are community shared food processing assets, let's say, would be the vector, because they already have some capabilities present. Okay, they probably have a connection to a power source. They have the space design already for that. They're known in the community. If we use this as a vector, let's say, taking into consideration their own economic model, that would be the sort of the target volume to be processed, which sets the sizes, right, of an extraction machine. I'm just trying to lay down the whole chain here, right? So let's say
I just think that the difference between grinding grain, which is what 10% moisture, and grinding leaves, or to 85%, it's really a whole different ball game. It's very I appreciate where you're going to utilize that model. It's already there, the community mill, but I don't think the grinding of grain is very closely related to what you'd be doing with leaves.
No, what I'm trying to say is that if you have, let's say, the core mill in the village, they're set up to process a certain quantity of stuff, which is the village capacity, right? And that would drive the requirements for the throughput of this machine, like how much stuff a village, how much leaves a village can produce per day to be processed, you know. So we're at that scale. That's what I'm trying to say. I'm not trying to say that this machine should process 3 tons of grains to be grinded, but at the same time also 3 tons of, it's just that we're fitting into that scale, because that's important for, you know, the dimensions of this thing. If this machine does not fit the economic reality of these places in a village, we might have a problem for adoption. That's what I'm trying to say. Okay, and if the requirements is a ton a day, let's say at max, and lower than 500 kilo is economically not viable, then that's our bracket, right?
And I mean, it would affect how much money you can spend on a machine. So, you know, if you were to say you've got $400 you can spend on a machine, or $800 or $1,000, that would have some impact on what you could use for a motor.
Yes, exactly.
And all kinds of things.
Yeah. So yeah. So again, this is the innovation is in the second in the second part. If we think of on top, if we based our thinking on this extruder design pattern, initially we started with some other ideas. The juice would be recovered at the belly of a first stage of an extruder, and then you know, we were brainstorming about ways to process that, put heat into it, and let it coagulate, and maybe have it separate by gravity first, and then scoop it and, I don't know, squeeze it somewhere else. So we were envisioning some other type of processes as well. You know, and yeah, this requires further thinking for sure.
I think it could be helpful to back to my sort of the sentiment I expressed a moment ago. If there's a possibility to have a short interview process or something, because if I think about referring to the village and the context, or the mill and the economic model, what's present in a village, and there isn't no single village, so different places, you know, what's the variation, what's the nature of the variation. I can just keep listing. There's so many things I know that the people that are here have answers to, that we don't have answers to, that would be critical information to help manage these trade-offs and make these decisions about scaling and size, and all strategies, even with detailed design choices. Some of the strategies like bracketing, what's the viable range of characteristics that you could design for, say, just to simply simplify your design problem by narrowing the space of considerations to what is even achievable. Just getting there, probably we could learn a lot from just a few questions at some point, but not to add that on to today. But I just feel like there's so much wealth of knowledge that could be being fed into the design, maybe.
Yeah, you know, we do have a list of questions here, and what thing we can do is to put them in a form of a form, and maybe distribute that.
Yeah, that's more efficient. Yeah, great.
Yeah, there's a bunch of questions that we have a lot of parameters, like basic parameters that we could start with, you know, at least for I don't know, some simulation of some basic small scale prototyping using 3D printers, because we have access to these capabilities.
Yeah, but on the divergent side too, I just want to mention, like when we talk about the hypothesis about the mill and the synergistic symbiotic kind of potential, that is an assumption, that there's an assumption being made there. Yeah, so not just a question and answer thing too, but maybe we can frame some of these categories in a more general way to invite clarification or informing around these things, like what else is in a village. There's this idea, you understand why this idea of the mill got mentioned. Well, now, you know, ignore what we've said, and based on all of the experiences that you've had, what are parallels, what are duals, what are other similarly strategic affordances within a village that could be capitalized on. So that sort of some open questions as well, because there's so much broader context awareness around some of the settings, and not to mention the detailed chemistry as well.
Yeah, Tim, we can think about how to deploy that, because there was also some thinking that we did and put it in a way that we can build on top, for sure. But essentially here we were asking the question, what are the food processing activities that are repeated almost every day by almost all the families in the village? And then these are the type of activities that are normally centralized by communities, like a corn mill. But the corn mill is just one example of that case, right? So in other villages, you might have some other things like cassava, you know, processing, or, you know, which is also an interesting thing. And by the way, if we solve this problem, this could be used for soy processing, tofu, could be used for cassava, you know, where you have a lot of liquid involved in the processes. So like Jay mentioned, you know, if you have if you have two phases and a lot of liquid and require some heat, you know, then I can see a similarity. So we're solving this problem for leaves, but that could be applied to other things. And I remember seeing a project which is called the soy cow, also dealing with the third world, and they have a batch process of making soy milk, tofu of all sorts of consistencies in a sort of a batch process. And their devices are not open source, but let's say they are built with that philosophy of low scale, low technical skills to use the stuff that you can put in a village in Africa. So I think there's a lot of synergy there, and we could learn stuff from them too, because although they use a batch process, they know the materials they're working with and the stages that they go through. They might provide some information. I don't
David, I just want to clarify. You said half ton. That's for the village scale. Is that half ton per day?
Yeah.
per day. Yes.
We almost always process half a day of grinding leaves, but it was hard to do it for more than 4 hours and still be able to get it done in time. But I'm sure it's different, and you know, we work very little in Asia, a lot in Latin America, so it's pretty different.
I would take a few minutes just to talk about the collaboration and the network of innovation that we're putting in place, because one of my goals with this meeting is to see if there is interest in more formal participation, right? And so how can we unleash these innovation forces to solve these technical problems that we just talked about, right? Is there any interest in going into that for 5 minutes, let's say? And
Yeah.
Okay, yes, because it's something quite unique what Sensorica is doing, right? So maybe it's worth looking at it. First, what is Sensorica? You know, we started this open network in 2011, and these are some metrics about the network. We have over 1,000 people engaging on Facebook. A mailing list, which is the direct way of communication. We have 190 people subscribed on a mailing list. We have 73 people subscribed on a messaging system called Discord. And this is a new communication tool that we essentially put in place when we started the project. Before, communication was mostly done with the mailing list, but this is the more direct tool that allows you also with video sharing and you know, chatting, and so it's very good for, let's say, synchronous collaboration. Talking about the project itself, you know, we have 18 individuals that have signed up to contribute to the venture. We call these contributors, and then we have a bunch of partners that have signed up for the project. 3 academic partners that we communicate on a regular basis, we have organizations that I have signed up to disseminate the project in Africa, South Asia, and South America. And we have 5 organizations that are waiting to be first users of this device. And this is only after 4 months of doing the project. Just another information before, this is where we are today. We are in what we call the first phase of consolidation of the project. So we started in March, where we did, maybe I should put this a little larger. We started in March. Most of the work has been, went into core network formation. So these core participants and the close partners for dissemination and the first users. So there was work through outreach and communication for core network formation. There was some institutional learning during this period. All these people learned Sensorica's mode of innovation and online collaborative work. And there was some work done on conceptualization. That's the scheme that we discussed on the technical issues, right? Why did we choose? How do we choose between an extruder or a batch process? That's what I'm talking about when I say conceptualization. We're now at the first phase of consolidation, which is after having contacted all these actors in the industry. We are trying to forge formal collaborations by different mechanisms, but the most important one is apply for funding together. So our team goes out there, finds grants, and then we go back to the list of the core network and think about compositions. Maybe there's a professor somewhere with a company somewhere with Sensorica that can partner for a grant. Now, once we have these new funding coming in and these formal relations, we go through the second phase of growth of this project. And this is the formation of what I call the innovation coalition, or the private public people partnership. And when we go full on the design and prototyping, okay? And then we will have a second phase of consolidation there, which means that the process is paused for a while to assess again the wealth of that new network. And this is where dissemination is going to start to kick in, and building of what we call an entrepreneurial coalition, meaning the local village corn mill that might adopt a leaf protein extractor that might have some other functions as well. These are entrepreneurs, and together we can form with them an entrepreneurial coalition. These are entities that adopt the device. So also the creation of ecosystem services to help these people learn how to use it, how to maintain it, you know, so on and so forth. So this is where the network expands to the next phase. Okay, once you have this innovation potential built, then you go through dissemination and the use of the thing. We believe that could take 2 or 3 years. And so having said that, how we work, essentially we can distinguish from how things are normally done. Okay, essentially a solution like that is designed as a commodity, as a product. Okay, so you have a private organization, a for-profit organization that instigates the project. and works in a public-private partnership model to get some new knowledge from, let's say, academia. This research can be in part funded by the private organization or by some governmental entities. That product can go out to an NGO and be distributed to local communities, or it can go straight to the user. That is the model, okay, that is normally used. So the solution is designed as a commodity. The private sector is at the core of the distribution, and then the innovation goes through a public-private partnership model. Okay, the social sector can intervene as well in the distribution and providing some feedback for innovation. The way we go about it is where is my slide? For a second. It's what we call the commons-based peer production model. Yes, it's right here. What we call the commons-based peer production model. So we have different players, different actors. The private sector is there with public institutions like academia, NGOs. They all work on a commons, which is the design turned into prototypes. So these are working designs. The community is there as a beneficiary. The innovation is, the innovation is it's not designed as a commodity, but it's designed as a commons, and that changes requirements for the design. Okay, it's made to be produced locally by very close to the user. Okay, by the user or by some special shops around the user. So since we're not designing it as a product, as a commodity, the whole innovation dynamic changes, right? So the private institution can supply engineers, funding, tools, ideas. Public sector can supply students, professors, tools, ideas. NGOs can provide ideas, can talk about, be ambassadors of these commons, and can provide networks, relations. The community can provide ideas as first users to the growth of these commons. And so that's how we think about doing it. And we talk about, on the innovation side, talk about private-public people partnership. Okay, this is how 3D printers work as well. Okay, 3D printers are devices that are designed to be produced locally. This is an example of the Prusa 3D printer. So it's an accessible object, right? Instead of being an exclusive object. It's open source 3D printers are not designed as a commodity. They're designed to be locally produced by the user or near the user. Okay, so we're based on the same model, saying that, you know, we can apply the innovation model of 3D printing to food processing. Okay, which was built through this commons-based peer production scheme that we're showing here, right? So where we are now is at this phase, like I said, of first phase of consolidation, meeting people like you and gathering resources together. Share funding is one of them, but then in order to grow these commons, we also ask, you know, participants to kick in some in-kind contributions, you know, and this holds together by a set of incentives. Why would a company get involved in feeding these commons without necessarily working directly on a product? Why would the university get involved? Why would NGOs get involved in these schemes? Well, first of all, this thing works. That's how the 3D printing was democratized. And that's how, you know, the 3D printing market is still in exponential growth. hasn't finished its exponential growth and adoption. It's still in that phase today, with new materials, new ways of, the metal sintering 3D printing process. The patent has just expired, so that sector goes into an exponential growth as we speak. So this is not something new, right? But what are the incentives? Just to look at them closely. This is a table that you can go back to, and you see what we as a network expect from these authors, from these actors, and what we think would be an incentive for them. Okay, so for example, NGOs, they could benefit from this project by getting new exposure, by acquiring new tools to help their missions, and to form new relationships with whoever is there, part of this project. We're also talking to intermediary organizations like innovation centers. These are in between academia and the private sector. Usually they're tech transfer hubs connecting industry to academia. And we think they can get exposure from these kind of projects. They can experiment new innovation methods and models, like the commons-based peer production one that we're setting up here. They can be exposed to new business models, and they could access new open innovation services. Equipment manufacturers, we have a few here. We can talk about corporate social responsibility. We could talk about exposure to through the communications that happen in this project. They can get exposed to new innovation methods. They can identify talent through this project in young engineers that are working on this extruder. So sourcing talent. And the same way you see in the 3D printing field, as the market is growing, you always find new opportunities for parts or products or services that it can provide to this market. And the academia is, process development, applications development. Somebody that, a university professor that works on processes can find through this project a way to apply it and go for new grants. Through our funding initiative, they can get new funding for their lab and students. It's a practical learning experience for students in an international collaboration setting, connect students with other students from other academic labs. So it goes into the same vein of international collaboration. So we think that there's enough glue here, and this is a pattern where just observing this in other fields, but there is enough glue here to hold an ecosystem like this, and this is precisely what we're building with this project. I don't know if people have some questions, maybe about intellectual property, like Dominic opened the. Dominic, we can't hear you. You're muted. Hello?
Yes, sorry, I have different screens and it's quite difficult to toggle in between. Yeah. Okay, thank you for this last part of your presentation, Tiberius. I think it was quite useful to summarize the specific interest of everyone into the project, and also to bring arguments to people to get them involved. I was thinking about manufacturer companies, because I'm still not fully confident how they would be interested to feed the project with their knowledge, with their expertise, and but I think it's something which is quite innovative and which shows the way on how we should try to work together. I think we are quite open to this public-private partnership, and because we already mentioned it for humanitarian purpose, but putting it into practice is still a big concern. And but I think we have here a case study where we could try to put this into practice, and especially if we could link it for our FHFST working group, if we could link it with our project in DRC, because we have a place where we could test the product, where we could test the whole concept on what we are talking before. How much is feasible per day in terms of leaves to process for a community. And I think it's a good introduction. And thank you, Tiberius, for the work you did, and for all the information that are included into the presentation. I invite all of you to browse the Google documents, because there are many information which are inside, many references. For example, you talk about Joshua Pierce, and then when you go to his page, you will see that he already published a book with many examples of open source hardware equipments that he designed, he developed, and which shows that it could be feasible. So I think we game over the time that we fixed for the meeting. So I think it's time now to close the meeting. What I suggest you, Tiberius, is what you said with Tim before. Maybe you could summarize some of the points, some of the questions that are still open and that would need some further collaboration, and then to share it with the group. And maybe if you had also in the same document some first thoughts on how we could participate to the group, to the collaborative teamwork that you set up. I think it would be helpful for each of us, because I think it's an approach which is quite new to us, both on an engineering side, and you have seen that there are still questions where we need to make some conceptual and practical work, but also in terms of organization, to make all those people work together and make it efficient. So as it's quite new for us, this way to collaborate, maybe you could add some very practical points on how you would see in the very near future the way that we could engage with your project. And I think it was quite useful at the beginning that we could each one could introduce, because now you have a good idea on the expertise and knowledge that everyone could bring, and how it could fit to your project. To your project, I could add another contact that I could bring to your project. In my laboratory, we have very good contact with a research laboratory in Canada at the University of Laval. And there, maybe I didn't have the opportunity to introduce your project to them, but we have a common laboratory with them. And maybe as they are much closer to you, it could be also some opportunity for them to work with you. So what I suggest you is that maybe you could share with us in the coming days or weeks a short document pointing the main questions that you see important to answer, and also the process that you would like us to use to collaborate with you. Are there other comments from the group? Jay, Dave, Pablo?
So it was very useful from my viewpoint, Dominic. I do agree, just a quick comment about the point Christopher made about the scale up and the business plan, the whole system, which is a point David made in his comments too, has to be looked into. From this discussion, it's very clear the technology solution we may end up, it may depend very much on the system and the scale. And again, as Christopher alluded to, we may not necessarily think about a fully continuous system, maybe a semi-continuous system where you have the first stage and you pump the liquid into a buffer tank, and then you pump that into the second stage. That will give you much more flexibility of not linking the two together. But that all depends on, are you talking about village scale or industrial scale? So before we do the details, I think that whole system has to be quantified. Who is going to use this? Who is the beneficiary, etc. And thank you, Tiberius. Very interesting. This open source is completely new to me, I must admit. So I learned a lot. I'm still not sure how it will all work, because these days, all the research providers have to recover their costs. Everything has to be fully costed. So I still can't see how the funding, the dollars flow into the system, where people, even in universities these days, people's times are costed, and it's just not in kind. So how that all works, I don't know, but I'm very interested to hear.
Yeah, maybe Tiberius, you could add into the discussion notes the link to Joshua book, because it's quite impressive, all the many examples that he gave and he could develop in his laboratory. And you know, this is the main approach is about this Fab Lab approach, this common place where different people can share experience and work together. And with this book, it shows that it's feasible even for technological matters, quite, and some of them are quite sophisticated. So if you have the link, maybe you could share it into the discussion note. And anyway, when I share the link to the recording, I will add it to the link, because it gives you a first overview of what we could do together, even at university level, because this guy is a professor at the Michigan State University. So you can do it at a university level.
I was wondering if you do you see the tractor that I'm trying to share?
Yes.
Yeah.
Yes.
Yeah. Just to, as a break, to give you an idea of Kesho Congo. They sent a lot of pictures recently in a report. If you're interested, I can pursue and on a few pictures. Is that all right?
Yeah, the idea that it gives me is that maybe you could use the engine of the tractor to run the extruder.
Well, the idea is really to give
Yeah,
you some contextualization of what's
yes.
happening in Congo
On
now.
the field. No, that's very, very relevant, and because it's very difficult to visualize what happens on the field, isn't it?
Yeah. So here they're working with communities of cooperatives and trying to. So I don't know if it should go all the way, but here we go. And then that's the result. They're growing maize because for doing their cookies, they intend to use only local product. And you know that in South Kivu, it's extremely difficult to rely only on local product because there's very little local production. All the food is imported from Rwanda mainly, which is benefiting of the situation. And they are running a war economy where people are digging in the earth all the rare earth and expensive metals, and including children going under the ground. And people cannot go in the fields anymore because it's very dangerous, but they can continue under the protection of the militias, going under the ground and work in to get some money, and then this money is used to import their food from Rwanda, Burundi, and Uganda. So this is a bit exceptional to, it's not so easy. There's some production local, but not as much as there should be in a very rich country in terms of quality of soils and a lot of water as well. So that's the team, part of the team of Kesho Congo. Here they're trying to grow some alfalfa, but it's not really successful, which is not surprising because the area is not too much water for alfalfa. And then some other, I sent them from various, oh, sorry, there's so many.
Copy, no?
Anyway, I don't even know how to go up again. Here we go. There's so many things in my screen. Here we go. Reddish brown, that's another leguminous that they're trying, which is supposed to be giving a lot of, it's a forage leguminous, not so many, not so much for the seeds, but for the leaves, grown for the leaves. And another one. And that's an interesting part. They're working on they are doing a training center. And in this training center, communication center, they will also have the workshop for doing for preparing the leaf concentrate, which you will see in a couple of pictures. So that's their work again. And they are doing this on their own. We are not even helping them for that. They just found some their own resources from the States and to do that. Okay. We send them some motoculture. I don't know, this sort of device, you know, to help working on the ground. Same thing again. Same thing again. And that's a cowpea. Yes. And that's they're collecting the cowpea, and there's a lot of discussion on how to collect cowpea. Is it collected? Do they just pick up a few leaves with the idea of preserving the seeds after for not the seeds, the
pods. Huh?
Say again?
The pods.
The pods and the fruits, let's say, or yes, the seeds, or do they cut all the leaves and expect for a second and possibly a third récolte, a third harvest. There's a discussion, and that's something which is under evaluation. You know, what is the best? Because of course, when you cut only pick up only the leaves, a few leaves, let's say 20% of the leaves, it takes a lot of time. It's difficult to be efficient. So here they come near the workshop, and you will see how rudimentary is their workshop now, and there's a lot of progress to be done. That's the equivalent of the equipment from Live for Life in Mexico that Dave sent pictures of. It's roughly the same idea. So for the mulching of the leaves.
The motor is an oil motor, right? The power
Say
source.
again?
It's powered by an engine, a combustion engine.
Yeah. Or I think in that case, how can I go? Yeah. It's strange because normally what they do is they run it with an electrical engine and they have a generator for the electricity. But it seems, I discovered this recently, that they have hooked a diesel engine directly to the grinder. And here they're heating up the stuff, the green juice, for coagulation. And here's the press. It's a bit messy, I would say. It's not as clean and efficient as the one that Dave was using in Mexico. That's the second stage of the pressing. That's the second separation, I think, between, but I'm not sure. No, that could be the first one, because the green juice is really green. Yeah, it's not whey, it's green juice. And here, that's a separation of the before the second pressing. And that's the so-called solar dryer. Actually, behind the two doors below, to accelerate the process, they are burning charcoal, so it's not really a solar system. There's a huge amount of progress to be done. That's why I wanted you to have a look at this. And this here's some grinding of the curd, the dried curd after, to make it before incorporating it into the biscuits. And here, one of the biggest achievement was to set up how do you say, a feeding center for the children into. It's highly successful because the demand is unbelievable. And that's Adolf Nekasani in the center, Dr. Adolf. And you will see the building in a while. It's in a very difficult place, very poor place, where they are making those biscuits available. Maybe it should be a bit less big. Yeah, okay.
Hey, Christophe, try to go faster because we.
Okay, yes, I'm trying.
Time is running
again,
short.
And we're almost at the end. And that's they also use porridge. So what they do is they put it in the little glasses, plastic glasses, and then they add the leaf concentrate to it before, and it was rather well accepted. So, and so much easier to do, of course. Nice pictures, anyway. They're communicating very well. That's there. And here we have we have the building in its environment, in the outskirts of Bukavu. Very, very poor. It's a slum actually. And here's the biscuits. That's how they do them. Yeah. The big ovens, they purchased from China. And here, that's the way they close the bags. I don't exactly know what this red stuff are. Peanuts? I don't know.
I think it's peanut.
Yeah. So they use different. That's the Dr. Mukwege, the
Nobel Prize.
with they collaborate with his hospital very close. So they're quite proud of this collaboration, of course. That's all. Yeah.
Okay, thank you, Christophe. I think it's time to wrap up the session. So, Tiberius, do you think that you could share in the coming days or weeks documents with the main questions that are still open, and also how you would see any future collaboration with the group?
Yes, definitely before the end of the week, for sure.
Okay.
Yeah.
So it was a bit longer than what we initially foresee, but I thank you for the one who was still online. I will send you the link to the recording if you want to share with other people interested to join
That would be nice. Yes.
the project, and maybe we, depending on your
It's a very good point. Interesting.
Okay. Okay, so thank you, everyone.
Yeah. Well, I want to also thank you, because we, together we realized that where the pain is and where the effort should go. And yeah, thank you for your expertise and your participation. Already this is big, because it will fit straight into the design, the 3D modeling, and we have assembled a team of engineers now to accelerate that process. So came right at the perfect timing for us, because it will inform directly what they will do. And
okay,
for sure, I'll be happy to have more participation in the future.
Okay, so thank you, everyone. Thank you, Australia. Thank you, USA. Thank you, France. And see you soon.